Welcome to the third video on gravitation. In this video we'll be looking at how we deal with Newton's law on a much smaller scale. So how it works for us here on Earth. So Newton's law of gravitation is valid when masses are particle-like. So that's when, as I said, that's when the radius of each of the particles interacting is much smaller than the distance between them. So when we look at objects on Earth, so in this case we'll look at our apple again. And from the point of view of an apple, the Earth certainly doesn't appear as a point-like particle. The Earth appears as a big flat ground that stretches from here to the horizon. So under those circumstances, we can't apply Newton's law of gravitation. And to solve that problem, we look at another one of Newton's theorems, of which he has plenty, and this is Newton's shell theorem. And what that says is that a uniform spherical shell of matter attracts a particle outside that shell, as if all of the shell's mass were concentrated at the centre. So we look at our Earth, and we look at our Earth as kind of a stack of a large number of spherical shells. So in the centre we have a very small shell, and as we go out those shells get bigger and bigger and bigger. And the mass for each of those spherical shells is concentrated in the centre of that shell, which is the centre of the Earth. So that we can say that using this theorem, Earth can be thought of as a point-like particle located at the Earth's centre with the entire mass of the Earth. And under this condition, then the two objects, the apple and this point-like particle, agree with the assumptions of Newton's law of gravitation. So using this assumption, let's find the acceleration due to gravity acting on the apple from the Earth. So step one is we draw a diagram. We have the mass of our apple, we have the mass of our point-like particle, that's our Earth, and we know the distance between them is the radius of Earth. And what we're looking for is the acceleration due to gravity of the Earth. The variables that we know are the gravitational constant, the mass of the Earth in kilograms, the mass of the apple in kilograms, and the radius of the Earth, so the distance between the two objects. We have two equations that we can use. We have Newton's law of gravitation, giving us the force due to gravity between two objects. And we also have Newton's second law, which gives us the force acting on a single object. So when we solve this, we combine those two equations and we simplify them. And this is a general equation, which gives us the acceleration due to gravity at a distance r from an object with a mass m. And then we simply plug in our variables into the equation and solve, and we find that the acceleration due to gravity acting on the apple from the Earth is 9.82 meters per second squared. And that is close to, but not equal to, the measured acceleration due to gravity on Earth. The difference is only small, that's 1.5% roughly, but it is still significant. So to understand why we get this difference from our calculated gravity compared to our measured gravity, we need to start looking at some of the assumptions that we've used. So we assumed that we were dealing with a point-like mass. And in order to do this, in our calculations, we assumed that the density of the Earth is a constant and also that the Earth is a sphere. And we know that the density of the Earth is not entirely constant, so we have things like rocks, water, magma. And we also know that the Earth is not exactly a sphere. And the Earth is spinning fast enough on its own axis that the poles are more flattened compared to the equator. So the Earth kind of bulges at the equator. And our second assumption is that Earth is in an inertial reference frame. That is, that the acceleration of someone standing on Earth is 0. And we know also that that's not the case, because we know Earth is spinning at a rate of knots, and so any object standing on Earth is experiencing a centripetal acceleration. So in the questions that follow this video, I will be asking you to calculate the influence of the centripetal acceleration on the acceleration due to gravity. The final case that I'd like to look at when we're dealing with Earth and gravitation is the gravity inside the Earth. So we've got our Earth here, and our Earth has a radius of capital R. And if we were to drill a hole through the middle of the Earth and place an apple somewhere in it, say at a radius little r, what would be the force due to gravity acting on that apple? So first up, we have Newton's law of gravitation. And there are two variables in this equation that will be affected by us moving the apple inside the Earth. The first of those is the mass of the Earth between the apple and the centre of the Earth. And as we move closer to the centre, that total mass decreases. So our force due to gravity should decrease. But likewise, as we move closer to the Earth, our radius decreases, and so our force due to gravity should increase. The second piece of information that we have is that the force due to gravity at a radius of capital R at the surface of the Earth is equal to gmm on r squared. And the third piece of information that we have is Newton's shell theorem. What we want is an expression for the force due to gravity as a function of the radius from the centre of the Earth. So by Newton's shell theorem, we know that the mass that the apple will see is the mass of the sphere with a radius of little r. So at that radius, we can write that the mass of the small radius is equal to the volume of the radius times the density of the Earth. And now we need somehow to relate that small radius to our known quantity, which is the force due to gravity at Earth's surface. So we know that the density is equal to the mass divided by the volume. Since it's a constant value, that's equal to the mass divided by the volume at any radius r. So we end up with this equation where we can equate the mass and volume of our small sphere with the mass and volume of the total Earth. And if we then substitute in the equation for the volume of a sphere and simplify, we end up with this equation that relates the variables of our small sphere to that of the Earth. And so now we can look at our equation for the force due to gravity at any chosen radius r. At this radius, the mass of the big object is equal to capital M subscript r, and we substitute then our previous equation into Newton's law of gravitation. And when we do that, we find that our equation for the force due to gravity at any radius r inside the Earth is proportional to r. And we know all those constants of proportionality. So we find that the gravitational force decreases linearly as the radius decreases. And we can further extend that to say we know then that at a radius of 0, so at the very centre of the Earth, there will be no gravitational force acting on any object. So since we can see that none of the mass of the Earth above the apple is exerting any force on the apple at all, we can make the corollary that a uniform spherical shell of matter doesn't exert any net force on a particle that's inside that shell. And that concludes our adventures into Newton's gravity on Earth.